This is actually work that I did for my master thesis, supervised by Valencia. You might have heard a bit about it in Příkovice, but it was only a small part of it, so this will be the whole thing. First I will show what I do on the case of translation of negation, and the errors in it and how I can correct it. This will show also the whole pipeline of DEPFIX, and then I will continue with details about how DEPFIX works inside, so the analysis it uses and the correction it does on the three layers: the morphological layer, grammatical layer, and tactogrammatical layer. Then I will say something about evaluation of DEPFIX, and in the end I will move to a partly different topic, which is parsing of machine translation outputs, which is actually a subtask of DEPFIX, but can be probably used independently. Translation of negation is basically the question whether we should use to be or not to be in our translation. And as we can see, machine translation systems can have problems with it. If you take a sentence, these are not actually errors. What Moses produces is souglásné chyby, which means these are actually errors. Whereas the correct form would be nejsou, or I would not cheat on you is a sentence that gets translated as já bych tě podváděl, or I would cheat on you. So I think we can see that it would be nice to be able to avoid such errors, because they might be quite serious. If you are a bit familiar with statistical machine translation, so the problem is in the different ways that negation is expressed in Czech and in English, where in English there is a separate token for it, whereas in Czech it's only a prefix, and when we do the alignment, so it can easily get misaligned and the negative particle may be lost. What can we do about it? It should be quite easy to fix that, right? Because in the source sentence we can see that there is the negation. In the translation we can see there is no negation here. We might even use the word alignment, and we see that the word not is left unaligned to anything. So it should be enough to just take the negative prefix for Czech and add it somewhere into the translation, and we're done, right? And sometimes this can really work, but usually it's quite a good idea to use some natural language processing tools to do it more correctly and to be able to fix various kinds of errors. Because here, for example, it's not so easy to detect that the negation is not there or that it is there, because it can be expressed in various ways, both in English and in Czech. It can be the negative prefix, but it might be using other words. And the same problem is that if we want to put the negation somewhere, so we need to know where in the sentence we want to put it. So maybe at the beginning, but maybe not. Okay, so the first tool that we are going to use is a part of speech tagger, which tells us the parts of speech of individual verbs. And this can help us in the negation so that we can negate the verb, the finite verb, because if we negate the verb, so we probably negated the sentence, so there should be a good idea how to do that. If we have fine-grained tags, such as the Czech positional tags, it can be even simpler, because the position in the tag can mark whether the word is negated or not. So this helps even more. To do it even better, we can use the Dependency Parser, which gives us the dependency trees of both the English source sentence and the Czech target sentence. And if we have the word alignment between the words that correspond to each other, we can just take the negation and project it through the word alignment to the verb here. So if, for example, it's a complex sentence with several clauses, we now know which clause to negate, and so on. We can go even further. We can use deep syntactic analysis, which, basically it will be the grammatical analysis, of course, which helps us to abstract from the various ways of expressing negation. So here, this is in the dependency tree are not, but on the deep syntax layer, we just can have attribute that tells us, okay, this node is negated, and we do not have to worry about the different ways that the negation can be expressed in. This is actually quite an optimistic view because the analysis to the tectogrammatical layer is not as perfect as that, so it needs some messing around, and this is basically the idea how to do it. Another tool, actually the last one that I will talk about, is a morphological generator, which helps us to generate new word forms. So we give it a word and some features that we want the word to possess, and it gives us the word form. So in Czech, it means that we give it the lemma and the tag, and it gives us the new word form. So we don't have to do something like, okay, we want to negate it, so we put there a prefix net. This might fail sometimes, but if we use the morphological generator, so we just give it to the lemma of so, which is feet, and the tag, which we negate by putting the n here, and we get the correct word form. So that's basically how it works. So the input to DEPFIX is an English sentence and its Czech translation, which we get from an SMT system, which might be Moses, Andrzej Boják and Aleš, which might be Google Translate or any other system. And we analyze it and we fix some errors in it. So we use both the morphological layer analysis, where we have the tags and the lemmas and the word alignment, and the A-layer analysis, where we have the dependency trees, then the T-layer analysis, where we have the tectogrammatical trees, and then when we fix the errors, we use the morphological generator to generate the corrected output. So hopefully the corrected Czech sentence. Okay, so moving on to the analysis and fixing steps. We'll begin with the morphological layer. So here we analyze both the sentences with lemmas, with positional tags, and with word alignment, which means which source words belong to which target words. And we found out that the automated tools actually do not work really well on the data we have, because it's data with errors. The machine translation outputs contain a lot of errors. So we usually have to do some post-processing of the outputs. So, for example, we have to add some missing alignment links, because the aligner expects that all the words get translated correctly, so then it is able to align them. But for example, if the translation system does not know the word, so it just stays the same. So it's obvious that this word is the same word, but the aligner has never seen that in its data, so it cannot align it. But it's easy to fix such things. And the four main types of corrections that we do on this low layer are projection of tokenization, projection of morphological number, true casing, which means putting correct big or small letters, and vocalization of prepositions. I'll show some of them. The tokenization projection is quite a simple thing. What happens is that in the source there might be something that gets translated just the same, but with different tokenization. So it's split into 3 tokens in the output. Sometimes it does not matter, sometimes it does. but usually it's better to keep the tokenization the same as it was in the source. So this is very simple to do just by matching of the strings. For example, here we can see that in detail, it's because when this token got analyzed only as one node, we could see that it belongs to this source token, and we could see that this is actually the subject of the sentence, and that there should be agreement between the subject and the predicate. I'll get to that later. An interesting thing is that when we evaluate DEPFIX with the standard machine translation metrics, such as the blue score, this is actually the correction that boosts the score the most, because blue is very sensitive to different tokenizations. So when I report some improvements, so maybe 1/3 of the improvement in the automatic score is by this very simple rule, which actually does not improve the output very much. So an idea is that you shouldn't trust these automatic metrics so much. Source-ware true-casing is another very simple thing. So if I take this source sentence, the director of the best hotel in Pets, Karel Rada, Moses does true-casing in a very stupid way. So it often happens that the words that are common in Czech get incorrect casing, so we could translate it as probably the director of the best hotel in Alden, which is not what we really want. But again, this is very easy to do because we can just do some string matching between the source and the target, and we can see, okay, when this was capitalized here, it probably should be capitalized here as well. There is a set of some exceptions which are capitalized in English but not in Czech, such as president, which is usually written with capital P in English but with lower P in Czech. So it's rule-based and there is a set of exceptions, but otherwise it's very simple to do. Localization of prepositions, this even does not require us to look at the source, because we have a tool for that detects cases where the preposition should or should not be vocalized. So it does not change the meaning, it just makes the sentence look better, and that's it. So this was the morphological layer. There are really simple fixes. Most of the fixes happen on the analytical layer, so on dependency trees with analytical functions. For Czech we had to use an adapted parser because, as I said, the outputs of machine translation contain many errors, and the basic parser is very sensitive to that. And I will talk about the parser at the end of my presentation. And again, we need to do some fixes of the outputs of the parser, because often it happens that, for example, we get preposition nodes that do not have any child nodes, which is in 99% of cases wrong. But because we know the English source sentence, so we can go through the word alignment to the English source sentence and try to find which words belong to that prepositions and move them to the prepositions where they belong. The inverse case is that auxiliary verbs sometimes get child nodes, which they shouldn't. They should be children of the parent node, content verb. So again, we can move that, other things like that, but that's more technical. The interesting part is the corrections of the sentences themselves. So we could divide it into two big categories of corrections that we do. One are agreement fixes, because in Czech there is a lot of agreement rules that are quite easy to obey, and unfortunately they are often violated by the machine translation systems. So we fix agreement between prepositions and nouns, or nouns and adjectives, and so on. I will show some examples again. Then there is something which I call fixes of transfer of meaning to morphology, which means, for example, that we can detect that something in English is a possessive, but in Czech it's expressed in a different way than in English. So we just have to find a way to extract the correct possessiveness of the word and transfer this meaning somehow to the target. I'll show again some examples which will hopefully make it clear. So one motivation sentence could be: all the winners received diploma, which Moses for some reason translated as všem výhercům obdržel diplom, which would be something like: to all the winners he received a diploma. And luckily DEPFIX is able to correct that, and I'll show you how. So this is the A layer that we work on. So this is the English dependency tree, this is the Czech dependency tree, so we can see all the winners received a diploma, and here it's the incorrect sentence, všem výhercům obdržel diplom. These are the word alignment links, the blue arrows, and we can immediately see a lot of errors, so let's fix some of them. So, for example, we can see that winners are the subject in English. We have the analytical function here, so it's easy to see that it's the subject. And through the word alignment, we can guess that výhercům should be the subject in Czech, which at the moment is not, because the case is wrong. That's easy to fix. The subject in Czech should be a nominative, so we change the case. We change also the analytical function, and we can regenerate the word form using the morphological generator based on the lemma and the tag. So, it's a bit better now. Lots more. In Czech there is noun-adjective agreement. So, všem výherci, it's not correct. It actually was kind of correct before, but because the head word was wrong, so this was in agreement, but it didn't help when we changed the head word. But again, that's easy to fix because we know that we require agreement in gender and case and number, and all these categories are in the part of speech tag, so we simply take these categories from the head word and change them in the dependent word so that it agrees. Regenerate the word form, and we're done. That's what we wanted. Still, it's not perfect, but we're nearly there. So the problem is here again: subject, predicate, agreement. So we already know that this is the subject thanks to the previous fix, and fortunately, we have correct label here for the predicate. So now we simply check the categories of these two, because Czech requires agreement in gender, number, and person between the subject and the predicate. So again, we can project the categories from here to here, from here to here. And now we have a correct sentence. So this is the core idea of DEPFIX. You analyze the sentence, you know some rules of Czech language, so you can find the errors, you can fix the errors, you can use morphological generator to give you the correct sentence, and that's about it. So now the rest will be just some details. Some more examples about the fixes that we do. Preposition noun agreement. So the source sentence is: it is a story about sport, race relations, and Nelson Mandela. And Moses gives us je to příběh o sportu, that's correct. Rastových vztahů, that's a bad case. And Nelson Mandela, that's a bad case again. It's because for the phrase-based machine translation system, the preposition "all" and the word "Mandela" are very far from each other, and it uses only short phrases, so it has no way to detect that, okay, these two belong together, it's too far. But because we have the dependency trees, it's very easy for us to do that. Actually, you can see that even the output is not perfect, it's better. Je to příběh o sportu, rasových vztazích a Nelson Mandelovi, so still the word Nelson should also be changed to Nelsonovi, but the morphological generator does not know the word Nelson probably, so it cannot generate the correct form. This happens especially with names, with named entities. It happens a lot. So it's not perfect. Maybe when DEPFIX will use the tool of MSD-Czech, it will get better. I don't know. Noun-adjective agreement. So this is what we already saw. It can have it can be changed in multiple words. So this half-hearted increase that the polovichatá nárůst. If the word is very rare, so then the machine translation system is happy enough to know at least some translation of the word, and it cannot generate the correct word form. But we can do that because, fortunately, our morphological analysis knows the word polovichatá. The problem is that the gender is feminine here, but it should be masculine because now it's masculine, so it just gets generated as polovichatý nárůst. There are some more interesting fixes that happen there, and that probably are not 100% correct in all cases, but even though help the translation. For example, it's a translation of. In English, of usually means possession. It's not always, so this is where we make a mistake, because by rules it's hard to detect cases where it should mean something different. But usually it means possession, like unsustainable deficit level of public finances, which is erroneous in here because it has a wrong case. So what we actually do is that if there is a noun and then a phrase which is a prepositional phrase with of, we think it's a possession, so we put it in the genitive case in Czech. The second case, so and we found out that usually this is the good thing to do. There are some exceptions, like we have to detect that somebody is talking about time, and then it's different, or things like that, but usually it works. This is a nice one, translation of apostrophe S. Again, the machine translation systems often have problems with it, because apostrophe and S can mean different things in English. Usually it's either the possessive S, or it's the contracted is. So in this case, we can see that Janota's possible continuation should be a possessive, but it got translated as if it were Janota is possible continuation, which is not correct. Luckily, we have the analysis of the English source sentence, where we get the English tag, which is POS. It means possessive, so it's very easy. We just delete the verb, because it shouldn't be there at all. And then we somehow have to make the possessive of Janota. Well, sometimes we are lucky and we can produce the word Janotův, but it's a name again, and we have often problems with names, so we have to do something a bit different. We create the genitive construction instead, so we change the word order and we get možné pokračování Janoty ve funkci. So in English it would be possible continuation of Janota, which we think that it's still better than to leave there the error, although it's not always perfect. Translation of subject, this is what we already saw in the trees, so another example where it's maybe a more serious error. At a time when Swiss voters have called for a ban on the construction of minarets, got translated as době, když švýcarské voliče vyzvali k zákazu výstavby minaretu, which kind of changes the meaning of the sentence, because it seems that the Swiss voters are the object and not the subject. But again, we know that in English this is a subject, so in Czech we can put it into nominative case, and we get the correct sentence. It's not perfectly fluent, but actually the meaning is definitely better. So this was the analytic layer. Now we also do some corrections on tactic-grammatical layer. So here it's the analysis to T trees. I prefer not to call them tactic-grammatical trees because we don't use most of the things about tactic-grammatical trees. We use form use most of the time, which are these things that tell us which case the words are in and which prepositions they have, and some of the grammar teams. But we, for example, are quite unable to use things like functors, because one thing is that the analysis of functors, the automated analysis of functors is not good enough. And the second thing is that actually for corrections of grammar, we don't need the functors so much. What we had to do in our work is to implement some systematic analysis of English verb tenses in trees. So if you need to analyze English verb tenses, so now it's much better than it was before. You usually get the actual tense the verb is in. And we do two types of fixes on the T layer. So these are again rule-based, similar as on the analytical layer, but we benefit from the instructions of the T layer. Negation was already shown in the motivation example. Then there are correction of translation of verb tenses, which gets translated very wildly in machine translation, because in English there are these compound verb forms, and very often the translation system just takes some verbs from the compound verb form, translates them somehow, and then we get some nonsense in the output. And pro-dropping is another thing we do. And then there are statistical fixes. This is the only part where DEPFIX is statistical. And these are corrections of Valencia. So actually only this part is what you saw in Příchovice. So the translation of verb tenses. So once we have the good analysis of the verb tenses, it's actually simple to do. We look at the English verb tense and the Czech verb tense. For example, here we can see this is future, but this is present, so that's probably not correct. It's hard to do that really reliably, because the way we use tenses in Czech is a bit different than the way we use tenses in English. And in English there is a wide range of tenses that they use, whereas in Czech it's much narrower range. But still, it's obvious that there are cases where the English sentence is in past and the Czech sentence is in future, so then it's definitely incorrect. So here it's really only an approximation. So we had to, or what we did is that we categorized all the English verb tenses into three categories: past, present, and the future, based on how they usually should be translated to Czech, and we changed the tense in Czech. Here we see, okay, this is future, so probably the best idea is to use future tense. And again, based on what our tools give us, sometimes we are able to generate. Here it would be to přinese problémy, but usually we are not able to generate that, so we just use the component form. Subject pronoun dropping is a nice thing. Usually, or maybe not usually, but let's say often, the translation systems translate all the subject pronouns literally, because, yeah, why not? It's usually not really a mistake, so it's probably the safer thing to do. But still what we do is that we try to drop the pronouns when it seems that they do not have to be there. We have again a set of heuristic rules which try to detect such cases, like if there is, for example, a coordination of several subject pronouns, and then we can't drop them. If we can see that they are somehow stressed, so then we can't drop them. But in a case like that, we can drop it. So já jsem nedivím, we can drop the já, we can get nedivím se. again, you can see that we not only drop the subject pronoun, but we also do some word reordering. This is basically to observe the grammatical second position, because here we have said at the second position, and it should stay at the second position, even if we drop the pronoun, so we have to move some other word there. So the some other word is the verb. And, yeah. Okay, now it's the time for Valencia. So again, I apologize to people who studied Valencia deeply, because our treatment of Valencia is very simplistic, but nevertheless it belongs to Valencia at least, and it can improve the translation quality, which is like the important thing with the names. So an example sentence: EU criticizes not only the Greek government, but translated by Google Translate, EU kritizuje nejen řecká vláda. So again, this the meaning is inversed here. It should be EU kritizuje nejen řeckou vládu, because here it seems that the government criticizes EU. I will show it on this example, and I will then tell that it's a bit broader, but you can now think about it as doing the subject-object distinction. And here, okay, we know that řecká vláda should be the object, because in English it's definitely the object, but still we do not know what to do. If we knew that something should be the subject, like EU, it's easy, we put it into nominative case, because subjects are nominative. If it is an object, so we maybe should put it into accusative, but maybe some other case, maybe in Czech it should even get a preposition. It can be varied. So this is where Valencia comes to place. So this is the sentence again, and let's look at the verb to criticize. Kritizovat. So in English, we can see that the frame of the verb to criticize is the subject, criticize is an object, and in English the subject and object are distinguished by their position. In Czech it's different, so there is again a subject and an object, but they are not distinguished by their position, they are distinguished by the morphological cases they are in. For the verb kritizovat, the subject is nominative, as usual, but the object is accusative. Right, so we need to somehow know that the object is accusative, and then we can correct the error. We are actually not interested in the whole Valencia frame. For simplicity, we decompose it into pairs of the head and the argument. So, to criticize the government should be translated as kritizovat vládu, independent on the subject of it, or in some more simpler terms, so to criticize an object in English should be translated as kritizovat something in accusative in Czech. So this is what we want to get, and probably we could try to get it from Valencia lexicons. We haven't tried it yet for several reasons, so we did it in a statistical way. So we do it on the T-trees, which are aligned and labeled with something. Actually, they are labeled with phonemes, so we know the parts of speech, and we know the subject and object in English, and we know the case in Czech. And yeah, it's easy to identify the head argument pairs, of course. And what we want to do is to correct the case here. So we train a statistical model for that, probabilistic model, which models the case of the argument, so here nominative or accusative or whatever, based on the lemma of the head, based on the function of the English argument, here is object, and for more fine-grained corrections, we also look at the lemma of the argument, so vláda. Because sometimes it's enough to look at the lemma of the parent and the function the word should have, and we already know the case. But sometimes for different words the cases are different. It might be because the Valencia frames are different, it might be because it's some fixed expressions, but because we do the statistical, we don't have to care about the reasons. We only use large data and we compute the probabilities, or we estimate the probabilities. We use Czech because it's large enough and it's available. And what we get is that here, if the head is kritizovat and the function should be object, so the estimated probability that the argument should be in nominative case is only 0.03, whereas the estimated probability of the argument being in accusative is 0.8. So this is exactly the information that we want. And we use some thresholds, so if we find an argument that has a probability of at least 0.55, it's just somehow estimated, we change it, so we change the case to the most probable one. Yeah, that's just again the sentence. This is the output where it was incorrect, it was used in nominative. We were now able to find the accusative case for vláda, which is love. And then this is just the agreement, the same thing that we did on the A layer, just the adjective and the noun should agree in these. Obviously this is a very rough way to do it, and often it does not work very well, but it works at least somehow. So it's there are many things that we could try with this thing to get it better. Yeah, it depends on what we will have to do. If we have, if I have time for that, so I would like to try more things with that. But yeah, I'm not sure about it. Yeah, some details about what we do. So it's what I said. It works on form use. So we can also generate and delete a preposition like the government spends on the middle schools, where we got vláda utrácí střední školy, which means something like the government destroys the middle schools. But again, we can identify the head argument pair. So in English it's spent on, and in Czech it's utrácet, and the fourth case, the accusative case. But the estimated probability of this pair is only 0.07. But we can find a better pair, which is utrácet za plus accusative, which gets a probability of 0.89. So we can probably safely take this as a better translation and get vláda utrácí za střední školy, which actually is the correct translation. The second detail about this is that I showed it on Verb Valencia, but we can easily model noun Valencia as well. For the statistical model, there is actually no difference whether the head word is a noun or a verb. So we just train two models, one model for verbs, one model for nouns. So from this experimental point of view, we are able to show that noun Valencia is a real existing phenomenon, and it behaves very similarly to the verb Valencia. This was all about how DEPFIX works. Now I will talk about the evaluation of DEPFIX a bit, and the rest of the time I will show the parser. So, when we use automatic evaluation, so as I already said, it usually does not work very well, so you can see that the differences are very small, even though we know that the differences actually are fine. So we use blue only when we don't have time to do manual evaluation, but usually we do manual evaluation. So this is the evaluation of the whole DEPFIX system as I showed it. It means that the annotators got it's about 1,000 sentences which went through DEPFIX, so they were corrected. So actually you can see that about 1/3 of them were not corrected, maybe because there was no error in them, or maybe because DEPFIX didn't find the error. And from the rest, from the sentences that were somehow changed by DEPFIX, in about 60%, the change by DEPFIX was positive. So DEPFIX found something which was actually wrong and changed it so that it was correct. So this is a nice thing. There is about 20% of cases where it actually made the sentence worse, which is unpleasant, but it's understandable. And then there are some cases where simply the annotators weren't able to decide whether actually the change was for better or for worse. Maybe because it was wrong, and after the correction it was still wrong, but in a different way. Or it can happen that the DEPFIX changes two things in a sentence. It improves one, but it worsens the second one, so then you cannot really evaluate if it improved the sentence. Cases like that. Now, this is the nice thing. It's from the WMT13 machine translation competition. It's an evaluation by humans. This darker one is by mechanical Turkers, so people who got some little money for evaluating. And this is by scientists, so by the people who create the systems. So you can decide whether you trust more the scientists or the mechanical Turkers, but the results are quite similar. So these are the three systems that, cooperated together from this faculty and were submitted to the competition. So it's the TEC20 syntax-based system, which sadly still does not perform very well. Then there was TEC20 plus Moses, which I can tell you more if you want. And then we used Moses enriched with TEC20 and post-edited by DEPFIX. And the nice thing is that, at least according to the scientists, this combination of all the systems was the best system in the whole competition. And definitely these two systems were the best. It depends on if you trust more scientists or mechanical Turkers. And the best thing is that we finally got better than Google Translate. The thing is that Google Translate is able to translate between some 50 language pairs or what, and we only do English-to-Czech. But still, we think that it's a success, and it shows that we are able to be the state-of-the-art in machine translation. Probably if we had as many people and money as Google does, so we could also do that for the other translation directions. It even got mentioned in the newspaper. You probably saw it in Valencia. It was 2 days ago. So, we also evaluated the individual parts of DEPFIX. And this is something like precision of the individual parts. From all the sentences that were either improved or worsened by the rule, we take the proportion of the ones that were improved. And we believe that we cannot really link the individual improvements to individual rules, so we do it on a sentence level. So if in the sentence there were 4 rules that changed something, and it was better in the end, so we give a point to all 4 of these rules, because it would be hard to do it otherwise. And the interesting thing is that when we did this evaluation, there were several rules that even didn't make it to 50%, which means that at least on the dataset that it was evaluated on, the rules made the output worse. It requires some tuning, and the systems, the machine translation systems are changing all the times. So something that works one year might not work the other year. It's varied, but still there is a lot of rules that are kind of high performance rules. The best one actually is the negation correction, which I showed in the beginning, because it changes the meaning of the sentence dramatically when the negation is there or is not there. And luckily it's relatively easy to fix that correctly, so we have some 90% precision in that. And yeah, actually the Valencia corrections are somewhere here, so they're quite around the 50% line, so it's obvious that they are not to be trusted so much at the moment. Another evaluation is the impact of the rules. It means how many sentences get changed by an individual rule. So here that's the number of the sentences from the dataset that were changed by these rules. Here this one is 5% of the sentences, so the whole dataset was some 800 sentences. And we can see that the largest impact has, the non-adjective agreement rule has the largest impact, because nouns are the most common word type, and adjectives are, I don't know, second or first. So it's very common that this can get fixed, because the noun-adjective pairs are very common in the data. Unfortunately, we can see that actually this rule is very close to this 50% precision line, but still it's above it, so still it means that overall it improves the translation. So then it's a good one because it can improve a lot of sentences. We can see some other rules. Some of them are a very tiny impact, like possessives or the preposition by or the preposition of, because this is not so common in the data, and also because it is often correct. We can see that the negation is really a good rule, because not only does it have a high precision, but it also has quite a high impact, which actually is a bad thing for the SMT people, because it means that the errors in negation are very common. And yeah, otherwise, these are the things that are unpleasant, because these are the Valencia corrections and the projection of noun number. So it means some idea that when it's singular in English, it should be singular in Czech. And we can see that this is usually wrong, and also it has quite a high impact. So it means it does badly, and it even changes a lot of sentences, so that's something that we should eliminate in further versions. But the thing is that when we do another evaluation, it's also always is a little different, so we are never sure about that 100%. It depends on the data, on the system, whatever. Okay, so the rest of the talk I will spend with the parser. So it's the parser that is used in DEPFIX to get the A trees, the analytical trees for Czech language. It's the idea is to be able to parse the outputs of statistical machine translation, which we use in DEPFIX, but which maybe might be used in other tasks, such as automatic classification of translation errors. Or maybe multilingual question answering, or whatever you want. And there are several things that are different when you parse machine translation outputs. One is that we have also the source sentence. Well, this is a good thing. We know something more about the sentence. But the basic parser does not use any other sentence, so we just want to include the information from the source sentence and give it to the parser so that it can parse the Czech sentence better, it can understand the Czech sentence better. The bad thing is that, as I said, the machine translation outputs are noisy, there are errors in them, in fluency, in grammar, but the parser, the basic parser, is trained on a gold standard tree bank such as PDT. So it does not know what to do when it encounters some wrong agreement because it does not appear in PDT, so it does not know whether it means okay, H should be there or shouldn't be there. So this is why the accuracy of the parser on machine translation output is worse. So we need to adapt to the noisy sentences somehow. We use the MSD Parser, the maximum spelling parser by Ryan McDonald, and we use the non-projected version. So this paper probably known to you. I will briefly show how MSD Parser works, but only very briefly. So let's imagine that the sentence is Rudolph relaxes abroad. We already have the cloud of speech text, and we want to get the dependency tree of such sentence. So what the parser does is that it adds there all possible edges. So it's a nearly complete graph, only the root is always the root, so there are no edges going from the root. And the idea is that the dependency tree of the sentence will be a subgraph of this graph. Then it assigns some weights to the edges. There is a large set of features, which is, for example, the feature can be, for example, the possible dependent is a noun and the possible parent is a verb. And because this is quite a good property for an edge, so it gets some positive score. Or it might be the distance between the words is only 1, they are adjacent to each other. So again, this is something that is usual for a dependency edge, so it will get a positive score. Or it might be something like that. The parent is the root and the child is an adverb. So this is not very usual. So it will get some negative score. And all these scores are summed together, and these are the sums of them, and then we just need to find the maximum spanning tree, which means a tree that has a maximum total score. Fortunately, there are already algorithms for that. For non-projective directed trees, it's the Tulio-Edmonds algorithm. If you wanted to do projective trees, there is another algorithm by Jason Eisner. And you use this algorithm and it gives you the maximum spanning tree of the sentence. In this case, it fortunately is actually the correct pass tree. And it's the maximum spanning tree because if you sum up these three scores, it's the largest sum of scores that you can get in this graph if you take a tree. And this is still unlabeled, so we then need the second stage labeler, which will give us the labels such as subject and predicate. So for DEPFIX, what we did is that we reimplemented this MSD parser in Perl. So if you need to use it, it's in trees. It's first order only, so it does not use some advanced features. And it's only non-projective, which actually is not a problem because you can parse even English with it, and if you are lucky you will get a projective tree, but it can happen that you get the non-projective tree because the parser does not know that the tree should be projective. So we implemented it and we adapted it for parsing of machine translation outputs in 4 ways. One is versioning of the training data, which was done by David, and the other are adding of parallel information, so something from the source sentence, then manually boosting feature weights and exploiting large-scale data, I will show it, So we trained it on track Czech English dependency tree bank because we need something that is parallel, that has both Czech and English side. And one thing we do is worsening the tree banks. Why worsening the tree bank? Well, the idea is very simple. The tree bank is perfect, but the sentences that we want to parse are not. So we need to make the tree bank worse so that it's more similar to the sentences that we are going to analyze. So we need to make some of these errors in the tree bank, such as incorrect word order or incorrect agreement, things like that. So we want to break it. But still we want to know the correct structure of the trees. So how do we do that? So we take the English side of Practical English Dependency Tree Bank and translate it to Czech by Moses, which means we will get some errors, which is basically what we want. So now we have the Gold English and the Gold Czech, which were in the tree bank, such as Rudolf Scarf is black and the Rudolf Bolte Czerny. And then we have a new Czech version from Moses, which could be, if it's really bad, Rudolf Bolte Czerny. Usually it isn't so bad, but whatever. And then we align these two Czech sentences together. We use the monolingual reliner by Martin, which has quite a simple task to align the same language together. So it can use some features that you usually don't use for two different languages, such as similarity of verb forms or lemmas, similarity of morphological tags, of positions in the sentence, and then just some symmetrization. Yeah, so what we get is that we now have the correct Czech sentence and the incorrect Czech sentence aligned together. So now we use it to estimate an error model. So we use maximum likelihood estimate for that, and we use the Czech tag set. And we want to estimate the probability that a correct tag will get changed to an incorrect tag in the translation. So, for example, a probability that the correct one is a noun in nominative, but instead we will see a noun in accusative. Yeah. So here. Yeah, there are some possibilities for the word linguistic scheme, linguistic, and these are probabilities that it will get wrong. For example, that it will have an incorrect number and case, the probability is 0.2, and so on. And then we take our gold check, so the Czech data from Czech English Dependency Tree Bank. And for each word, we sample a new tag. So with the largest probability, it will be just the original tag, the correct one. But with some probabilities like that, the word will get a new tag which will be incorrect. Then we can feed it to the morphological generator. So we get a new form which is incorrect. And this is the worsened Czech. So then we have Gold English worsened Czech parallel tree bank. The good thing is that we only change the individual words, so we can still keep the same tree structure. This is important because we want to have the gold trees, the correct trees, but the incorrect sentences underlined. Simple thing is using the parallel features, so including some information about the source sentence. So we use word alignment for that, so that we know which words correspond to each other. And if a node has an aligned node, so if for a Czech node we have an English source node which it corresponds to, we look at three things. We look at the tag of the English word. We look at its dependency labels, whether it's a subject or object or what, and then aligned edge existence, which basically means whether the edge that we are trying to make in Czech exists in English. I have a picture for that. So imagine that we have Rudolf reaguje zahraničí, the sentence in Czech, and we don't know this parse tree yet. We want to construct this tree, but we don't know it. But what we know is the English sentence, Rudolf relaxes abroad, and its dependency tree. So for example, if we want to make this edge, Rudolf reaguje, so for Rudolf we can look at its tag in English. For the edge we can look at its label in English, and most importantly we can see that this edge exists in English. So it's probably quite likely that the same edge should exist in Czech. We cannot do it in a rule-based way, so that we would simply copy the edges from English to Czech, because of differences between English and Czech. For example, relaxes and abroad. In Czech, this is reaguje zahraničí, and actually there is an edge between relax and abroad here, but it does not mean that there should be an edge between reaguje and zahraničí, because in Czech we have the preposition in between. So we only put it, we only add it as a feature for the parser, so it will get some probabilities and hopefully choose the correct thing. Yeah, this is quite a hack. This aligned edge existence is the key feature where we project the English tree into the Czech sentence. And we found out that maybe we should do the projection more aggressively. The feature got a score which is minus 0.57, and we actually decided to make the score larger so that it propagates this idea that the trees should be the same, and it helped. So the idea is that even if you have some crazy probabilistic thing that has a lot of some probabilities inside, you can still go directly to it and change the numbers, and maybe it will help. If you cannot change the data so that you have the same data that you are expecting, you can just hack it somehow and it can help. Basically we just try different values and chose the best one. Okay, and the last thing that we use in the parser is exploiting large-scale data. Why? Well, lexical features are important for the parser. We can do parsing only looking at the part-of-speech tags and the position in the sentence, but still this will not be as good as if we look also on the lemmas and on the word forms. So we need to have these. But if you look at Czech, it has 10 times more lemmas than PCEDT. In PCEDT there are only 40,000 different lemmas, whereas in Czech there are 400,000. The good thing would be if we would just train the parser on whole chain, so we would get all we can, but that's infeasible because we would just wait for the parser to train forever, and the model will be very large and it would not be useful actually. So we just inject this lexical information in a different way. This is by computing point-wise mutual information. So it's something like the probability that if two words appear in the same sentence, there should be an edge between them. And we do that only for the lemmas. So instead of having all these different features about tags and position and everything, we have only one new feature which only tells us the mutual information, the point-wise mutual information of the two nodes. And this is something that we can do effectively. We process the whole chain separately, and then we only extract these numbers from it, and we give only these numbers to our parser during training. And it turned out that all of these improvements helped. We looked at some of the parse trees, and we saw that, for example, now the parser is able to identify the subject of the sentence even when the subject is not in nominative, because this is what happens in machine translation outputs, or that it can get correctly the adjective noun edges even if the agreement is violated, which is good because then we can correct this alignment in DEPFIX, but we need to have the edge there. But the evaluation is hard to do reliably because what we are actually trying to do is to find a correct parse tree for a sentence that is incorrect. So such a task is not well defined. Because if the sentence is incorrect, no theory will give us the correct parse tree for the sentence, because actually it's hard to say what the sentence should mean. But what we can do is that we simply use different parsers in DEPFIX and see whether it helps to change the parser. So we did a similar evaluation to the evaluation of DEPFIX itself. So what we did is that we put our new adaptive parser into DEPFIX and we compare the outputs to the case where we used either the original MSD Parser by Ryan McDonald, or where we use our baseline parser, so just the reimplementation without these 4 improvements. And in both cases, using the adaptive parser turned out to be better, which we measured by the thing that the corrections that the rounds of DEPFIX differed in were usually better in the adaptive parser case. So more than a half of the sentences that were different in the outputs of the DEPFIX with the adaptive parser and the DEPFIX with the baseline parser. So more than half of the sentences were better when we used the adaptive parser. Okay, so that's everything. So I showed you how DEPFIX works on translation or negation. I showed you the fixing pipeline, which is analyses to M layer, where we have lemmas, text, and word alignment, and we do some simple fixes. Then analyses to A layer, when we have also dependency trees and analytical functions, and we can do a lot of fixes, even some advanced ones. And then the analysis to T layer, where we have form teams and grammar teams, where we can do some really wild things. And I showed you the results, and I showed you the MSD Parser, which is kind of independent of DEPFIX, but I think currently it is used only in DEPFIX. Okay, thank you for attention.
Thank you very much. This was a very nice piece of work. And actually, it reminded me of one story which I can't resist not to tell you. Some 40 years ago, when maybe 35, when we started to work on machine translation from English to Czech, we had we had to prove or demonstrate that the money we get from the state for our research is a well-deserved sum of money. So there were some inspections coming from the Ministry of Education, which places. And then we have to provide some tests of the translation, of the machine translation from English to Czech. And I also should give the name of our main developer of machine translation. It was the late Zdeněk Kirchner. I see here maybe 4 people, 1, 2, 3, 4, 5, 6 people who still remember him. He was a very nice colleague, I must say. And once when we had to run such a test, the input sentence was, this is not a very intelligent machine. So it reminded me of your negation example. and the Czech output was to je velmi inteligentní stroj. So it's exactly what you have said, and you can imagine that the machine was translating a sentence which was a negative appreciation of the machine, and on the output there was a positive appreciation of the machine. So this is one of the stories which we have. It's machine translation from English to Czech, and I think it's exactly in the context of what you were telling us. So now questions, more up-to-date questions. Yeah, please.
Thanks for the nice talk. I was wondering, how did you decide the order of the fixes? Because I can imagine cases like, okay, let's fix the agreement between adjectives and nouns, but then I go ahead and fix the noun because it doesn't agree with the verb. And suddenly what I fixed before is wrong again. Is there a specific order that you
Yeah, that's definitely a relevant question. Thank you. You are definitely right that the order of the application of the rules is important, because we saw it even in one of the examples where we first fixed the subject and then všem became incorrect and we had to change it to všichni. And so there is a fixed order, and what I did is that I basically inspected all the dependencies between the individual rules, and I draw it as a graph, and I found the topological ordering, and there was one, so there are no cyclic dependencies among the rules, so it is possible to do such an ordering of the rules that you apply each rule once, and the way they depend on each other is not violated. Actually, for some time I had one rule that violated this, so it meant that I just used to apply some rules twice. So once, and then this rule, and then again the same rules, because something might have changed. But in the current version, it's okay. Thank you.
Thank you. Ante.
I might have missed that in your presentation, but if you are getting conflicting information from the, for example, the agreement between the subject and the predicate, and then the number is in a mismatch. How do you decide what to trust more? Obviously there is the source, but still the source may be different from what the check needs. So,
yeah, that's a good question. So basically you always either have to choose the head or the dependent as the authoritative one and use its categories for the other one. And we just tried the two possible ways, and we chose the one that showed to work better. So one thing, usually it's the parent, the governor, because one thing is that the rules also go basically from the root to the leaves. So first we have to fix the predicate, and then first we have to fix the subject and then the predicate. But then we just go to the dependent nodes. So once we fix the subject, then according to the subject we fix its adjectives and such on. Yeah, I think it might be a good idea to do something more clever, to somehow decide individually for each occasion of fixing which one is to be trusted more, which is something that we don't do at the moment. But it might be helpful. Usually it seems that it's clear for some reason if you have an adjective and the noun, so usually the noun is correct and the adjective is not. I don't know actually why, but it works like that. So I think the only case where the dependent node is authoritative is the subject and predicate. So here we look at the subject. Because such things like the gender of the subject, we probably cannot change that, but we can easily change the gender of the predicate. The number of the subject, again, is quite easy to get from English if you want, but the number of the predicate, that's hard. Because in English, if it's not the first person, you cannot see whether it's singular or plural. So it's fine.
And do you have any plans to move from rules to statistics, to training the first part? Because that would also allow for more language independence.
Mm-hmm. Yeah, that's definitely one of the plans. It was actually suggested by Zdeněk. And yeah, now it's very English-Czech translation dependent. So the idea is to try to make it somehow machine learnable. So probably something like how it's called. I forgot the name of it. When you learn some rules from the data.
Data-driven rules.
I think it was used, for example, in Braille's tagger, where it actually learns some rules from the data. So something like that, but yeah, I'm not sure now. I'm nearly sure that just using some simple statistics is another good way, because that would be nearly the same as the SMT systems do. So now we benefit from the thing that DEPFIX is kind of orthogonal to the machine translation systems, because the typical machine translation systems knows nothing about linguistic and just has some statistics. So what we do is that we put in a lot of linguistics and don't use statistics. So this is actually why we are able to improve the machine translation. It might be also said that when we try to run DEPFIX on the outputs of text-to-MT, which is very linguistical, it doesn't improve the outputs. We run DEPFIX on outputs of maybe 20 different machine translation systems, and text-to-MT is the only one where the results after DEPFIX are always worse.
You mentioned in your talk that 45 sentences are not changed by DEPFIX. So I would hesitate to say that 45% of translations are correct. I assume therefore that there are still some phenomena that you don't capture. I'm wondering if you have future plans for it. What are the phenomena that you would like to work on next?
Definitely. Yeah, we did an error analysis, so we think that we capture the most serious errors or the most common errors. What we definitely don't capture are lexical errors, because this is basically a grammar checker, just very clever. But the main thing it fixes is grammar. So if there is a problem in the meaning, like a lexical choice is incorrect, this is something that we don't do. Probably the best thing for lexical choices currently are SMT systems, and if they don't get it right, so there is no help. And then there are other things like we currently do not use coreference features yet. So this could be used for agreement, like, I don't know how it's called, like coreference agreement. If there is a pronoun that refers to a noun, so it must have the same gender, for example. So we don't do that yet because we don't, I don't know if we already have a good coreference analysis now, but we didn't before. So maybe now we need to try that.
I have one question, but it's possibly not a question that should address you, but more the Moses people. I actually was surprised by some of your examples of the wrong translations by Moses, that such a translation could have been produced, especially in the case of the subject to be not in the nominative case, because subject in English precedes the verb, so at least for me, it would be the first translation would be nominative that I see on with this face. Okay, so many thanks. I think it was a very instructive talk, and I should say that we don't have our seminar next week and the week after for some very obvious reasons. I mean, next week there is a Platin meeting in Prague, and 7 people, maybe even more, from our group will attend that meeting, and there'll still be some people in Japan for the conference, so the audience would be very, very restricted. And the week after we have our state holidays. So the next seminar is on November the 4th. But I would like to ask you, at the Platin meeting in Prague, we have one prominent colleague coming here as a member of the advisory board of Platin, and that's Ed Hoge. He will be here, at our disposal, so to say, on Wednesday, so not this Wednesday, but the next Wednesday afternoon. And the invitation for him was that he should come here to my office or to Jan's office, and we can talk together. He might be interested in what we are doing, and we might be interested in what he is doing. So if there is somebody interested in talking to him on Wednesday afternoon after 4 o'clock, so let us say between 4 and 6, please let me know. Please send me a message, and I can arrange for that. So that's just, you can take it as a replacement of the seminar next Monday. And in any case, we'll meet here, I hope, on Monday, November the 4th. Okay, so thank you very much once. Thank you.